Good morning, everyone, and welcome. I'm Antonio Marcomini, Deputy Rector of the Ca' Foscari University of Venice. Rector Tiziana Lippiello sends her warmest regards and her apologies for not being here today. She's currently traveling in Japan, which made rescheduling unfortunately impossible. It is my great honor and pleasure to welcome Professor Carl Wieman to our scientific campus. Professor Wieman received the Nobel Prize in Physics in 2001, but what makes his visit especially meaningful to us today is what he has been doing for the past 20 years, applying the scientific method to the question of how people actually learn science. His research has produced some of the strongest evidence we have that university teaching can be dramatically more effective than it currently is. That message is very important for any university, and Ca' Foscari takes it quite seriously. Thank you very much to Stefano Bonetti, who is the organizer of the visit. And now I'll give you to you, Stefano, the floor in order to add more context and details about Carl Wieman. Again, thank you very much, Carl. Thank you very much, Stefano.
Thank you, Antonio. Thank you, Carl, for being here. It's a pleasure and an honor to have you here. And I have to tell, I first encountered Carl by chance when I was at Stanford. And you organized a seminar for the postdocs. I was a postdoc there. And I remember, if I remember correctly, you were surprised by how many people showed up at the time, because it was a workshop on education. I was going to become a faculty. I wanted to more. I read the abstract. I found it very interesting. And the room was full. Like, hopefully, I'm very happy that this room is full today as well. And the seminar was impressed so much that actually I decided I have to teach the way he was discussing. So when I became faculty, first at Stockholm and then here, I tried to implement these methods. And since we study engineering physics here at Ca' Foscari, several of us on the campus have started to implementing these methods in our courses with extremely good results. But the next step, what we want to do is to design an entire curriculum with this method. This is something that, according to Carl, if I understood well, no one has tried. So we want to try this for the first time to do the entire master in engineering physics based on evidence-based methods to teaching. So this is something that hopefully will inspire others. So it's not only engineering physics, we have computer science, we have chemistry, we have environmental science, we have many courses here where I think this method could be applied, and I hope this seminar will be interesting, because this seminar is not about the transformation we want to do in the course, but about hearing directly from the person who started or was one of the pioneers in this field of research. How do we have to teach? And I advise you, this talk will challenge some of the assumptions about how we teach, which I found very amusing sometimes, and I like a lot. The way that some of the assumptions that we always believe to be true, they are not. And I think this is exactly what we need, to be a bit more challenged and to see, to really use the scientific method that we use in research also in the way we teach. So thank you, Carl, for coming here, and the floor is yours. Thanks.
Okay, I just need for okay, great. So I'm going to talk to you about kind of taking a scientific approach to learning and teaching science and engineering. And many of you may not be in science and engineering, and for you, I'll just say that I think a lot of what I'm going to talk is just principles about learning that apply very generally. And in fact, I don't see that we want all students to be scientists, but I think it's a basic scientific literacy is important for every student really in the modern world. That sort of knowing that way of thinking and some of that knowledge, it helps make people make better decisions in many different aspects of their lives. So the goals of this talk are for the teachers to get new insights about teaching and how to do it better. Many of you are students, and so for you, the goal is really to understand what you need to do to learn better and more efficiently, and also you can evaluate the teaching you're getting better. So the talk is organized today in terms of first a general introduction, just about how the brain learns complex thinking, and then focusing down, applying these ideas in university classrooms and measuring some of the results, and then get into even more details really about what research shows improves learning and why. And then I'll say a little bit at the end about AI in education, just because everyone's interested in these days. But before I start, I want to give you a little background about how I got involved in the education and sort of my perspective in thinking about it. And it actually started with my, working with my PhD students in my atomic physics research lab, and being struck by a pattern which I saw, which was these students would have many years of success in physics courses, but when they came to work in the research lab, they really didn't seem to know how to do physics. But there wasn't anything fundamentally defective about them, because after just a couple of years working in my lab, they'd turned into good physicists. And so after I saw this happening, repeatedly over and over again, I decided there was a fundamental question here about, so I treat this really as a science question, looking at what do we know about how people learn, particularly how they learn physics, to try and understand this pattern. And, after a few years of reading lots of research papers, I came to basically understand the reason this was happening, explain this puzzle. And I realized there also were much more effective ways to teach than was being used in most of our university courses. But it also then got me started on doing research in science education, doing experiments in classrooms, collecting data on the results, and looking for guiding principles that could understand how to do this better. But always an overriding sort of perspective I've always been interested in is expertise. What I mean is thinking like a good scientist and engineer, what's involved in that kind of thinking and how is the best way to teach it. And it's helped that over the past few decades, there's been actually major insights from research on how to do how to teach this kind of complex thinking better. And it's come from three different complementary areas. There's the cognitive psychologists who mostly in the laboratory study basic things about how people think and learn, brain research, and then people like myself, university faculty members in science and engineering, doing experiments and collecting data in their classrooms. Now, just want to say that most of the data we have on this comes predominantly from North American universities, but I think you'll see the general principles that we have that give us much more confidence these apply much more broadly to other countries and across the world, other cultures. And we're now getting increasing amounts of data from other places of the world that show a very similar pattern to what we've had. Okay, so let me start out by what the research has told us. And the most fundamental thing is really rethinking how learning happens. And the old and still very pervasive current model at university level is that the way thinking happens is these students' brains come into our classrooms and they vary in different ways, and we immerse them in knowledge, and then that knowledge sinks into different amounts depending on the condition of the brain. And so with this as your model of learning, then the focus is usually on thinking about how you're going to select the brains that'll soak up knowledge best, and then what to put in the curriculum, what topics to cover in what order, and so on. Now, I say this is a very pervasive model of filling brains with knowledge, but it's also just wrong. That research gives us quite a different view, which is that these brains aren't all that different, actually, at the university level when they come into the classroom, but they're really transformed by the educational process. In fact, the neurons are rewired, how they're hooked together as a result of the intense thinking they do as part of their educational process. And so you're really developing new capabilities in the brain, and that's really what learning is about. Now, you can actually see this in modern brain imaging. This is the brains of two people who are in an MRI machines interpreting x-rays. And on the right is a medical student who's just learning how to do this. On the left is a highly trained radiologist who's spent many years learning how to do this better. And you can see how their brains are activated in completely different ways as a result of the training that one has had. So, what the basic idea of brain research is telling us that learning is really about enhancing the relevant neuron connections. And the brain mostly learns what it practices and not much else. And so it's really much more like muscle development than we used to think. And so just like if I want to build up a muscle, the type and intensity of exercise is critical. If I want to develop the brain, the type of mental exercise, again, is critical. And, if you just to wonder about why this old ideas have been around and accepted for so long, this traditional view of learning, is that, I think in a way it's kind of surprising, because if you look at something like music or athletics, no one would think you could become a skilled musician or athlete just by listening to someone tell you how to do it, listening to lectures. And so, it's surprising they think that should be true for science. In these fields, the need for practice at actually doing it is quite obvious. And so how come people don't recognize this for science? Well, there are a number of reasons, but one of the things that I think is important is that it's because the level of performance in something like athletics or music is really obvious. It's really clear when someone's good or worse at this. And so you can easily measure what works, and you can even measure then what's important for learning and getting better and see how it works. Whereas in thinking, thinking scientifically and so on, that's a much harder thing to measure. And so it's harder to see what kind of practice or teaching is most effective there. And so that's really why people can have the wrong ideas about teaching. But, the great thing about research, like I and others have been doing, is that we've been finding better ways to thinking, and therefore we can find better ways to measure what kind of ways to teach work best. And so I'm going to then switch to start talking about, okay, so what has this research showed us? And the first is kind of knowing what learners need to do to develop expertise, expert ways of thinking. And this is really true for any subject. And this is work that's been pioneered by Anders Ericsson, who's studied expertise across many different fields of activity. And he's found that universally this developing expertise, particularly to a high level, thinking like a scientist or engineer or a good physician or a great chess player, it requires a very particular kind of practice, and that he calls deliberate practice. And the components of deliberate practice are, first, it's not just routine, low-level practice or experience. That doesn't work very well for developing expertise. It's a very intense, fully concentrating effort at at getting better at the task. And so this is intense effort focused really on improving your expertise, particularly the sub skills that make up the field of expertise. And so in science and engineering, the thing you need to practice, the thinking is really solving problems and figuring things out. That's what scientists and engineers do. And like I say, it's true also for many other disciplines in a related way. Now, he's shown that it's very important that this practice thinking that you need to do has to be challenging. It has to be difficult, that the learner really is getting pushed to this. If it's not, their neurons don't get hooked up in the right way. And so, this message to students, if it's not hard, if it's not, you're not sort of struggling, you're really probably not learning really very much. And it's because you're sort of practicing very challenging tasks, it means you're sometimes going to fail, and that's just got to be accepted as part of the learning process. Now, it's not enough, Erickson has shown, it's not enough just to practice something, although that, is critical. There's also needs to be feedback, usually from a teacher or coach, on how you're doing, what you're doing right, but also what, most importantly, what you can do to actually improve. And the thing seen is that motivation is really important. This learning, this effective learning is inherently very hard work. It takes a lot of mental effort. And so the learner has to be motivated to put in that effort. So this is something both the learner has to focus on and the teacher as well, just to motivate the learner to put in all this effort. And what Erickson has shown is getting beyond just the very beginning levels of expertise, the amount of high quality practice one gets is really the primary determinant of what one's level of expertise one reaches. And nothing else matters nearly as much. So things like measures of talent and so on are really not very important compared to how much of this kind of deliberate practice one actually takes. And so this is a quick summary of basically what the learner needs to do to develop expertise in a subject and what the teacher needs to facilitate. So now I'm going to move forward, though, and talk about applying these deliberate practice ideas in university classrooms and measuring results. And I've actually applied this in now quite a number of courses and collected data on the benefits of the amount of improved learning compared to lecture approaches across many different courses. And I'm just going to give a few examples here. The first is taking a large introductory physics course, where it could take two large sections that were very nearly identical by lots of measures and compare teaching in two different ways. And so one of these was called the control section. It was taught by a very experienced professor who had good student ratings, but used a standard lecture approach. And the experimental class then was taught by someone who is a fairly new physics PhD, but had been trained in my program in these research-based methods of teaching. And these two instructors agreed to cover the same set of material in the same amount of time, and then to both sections give a surprise test just to see how much they'd learned from their classes. So I assume most of you know how the standard lecture class works. The professor is talking, the students are listening, maybe taking notes. The experimental class is quite different. The students had a short pre-class assignment that they prepared ahead of class, giving them some basic facts. And then class would involve them answering questions and tasks. And so here's an example of a question posed to the class. You have a circuit with light bulbs and a battery, and when you close that switch, the students are asked, what's going to happen to the brightness of bulb number 2? And in this case, every student has a device that they can use to answer this, what they think the answer is to this question. When this was done, there was devices just devoted to this called clickers. Nowadays, that's largely replaced with mobile phones where students do the same thing. But the result is the same. Each student has answer what they think, the right answer is, and then the instructor's computer records who they were and what answer they chose, and can display it for what the whole class selected. Now, after the students vote, though, they aren't told what the answer is. Instead, they're told to talk to each other, to their fellow students. In a big class like this, it was be just their neighboring students and the seats around them, to discuss what was the right answer and why, and then they re-vote. But while they're doing that discussion, the instructor isn't just standing around waiting for them to finish. They're circulating around in a big lecture theater like this. They'd be going up and down the aisles, listening in on those student conversations, getting little snapshots of what's going on in the students' brains, what aspects of their thinking is desired and where they're confused. And then the instructor would demonstrate what would happen, sort of show them a result. And then, very importantly, there'd be a follow-up summary by the instructor, giving them feedback on which models and reasoning was correct and which were incorrect and why. And I emphasize that because this is really where most learning takes place, is when someone thinks about something incorrectly and then is helped to understand why they were incorrect and how to change their thinking. Now, you can't do everything, and certainly not in physics, with multiple choice questions. So for more mathematical topics, the students would actually have to write things out on worksheets. But again, the same idea, they would be talking to their fellow students as they were doing this. The instructor would be monitoring what they were doing. So if you think about what's going on in the students' brains during an activity like this, they're practicing thinking like physicists, the kind of thinking you want them to learn. They're doing it because they're having to choose a conceptual model for electricity, test and apply it to this particular case. And as they're doing that, they have to critique their own reasoning and their reasoning of their fellow students. And so this is all kind of, the thinking that physicists do. Now, but as they're doing that thinking, they're getting feedback from multiple sources to help them improve their thinking. They're getting it from their discussion with fellow students. They're getting it from comparing their prediction with what actually happens in the demonstration. And they're getting it from this informed instructor feedback. Okay, now remember, this was an experiment. And so there was an identical quiz in both these two sections. And here's what the results look like with the histogram, so the test score versus number of students. And you can see the experimental section in blue, the students scored much better than in red. And in fact, on this particular quiz, the random guessing would give a person about 3. And so the amount of learning is sort of how far above 3 you are. And when you see that, you realize that the amount of learning from the lecture was really tiny. And this is consistent with other measures we've gotten. But the other point I want to emphasize here is that the entire distribution is moved up. So this is a way of teaching that's not just good for the weaker students or the stronger students. It's really good for the entire population of students, lives better learning. Okay, so that's one example. This is an example from a different subject. This is computer science, and it's a different measure of learning outcomes. Here, they measured the drop in failure rates from the course, looking over the entire course. And in this experiment, it was 4 of the core computer science courses done at UC San Diego. And they had the same instructors teach the courses, but the one year they taught the standard lecture approach, and then the following year they taught a sort of research-based approach, which used very much what I just described for the physics of giving students questions they had to answer and discuss amongst themselves and so on. And they looked at the drop in failure rates there for then the subsequent year taught in a different way. And those are in green. You can see they're all much lower. And so this is a case of having the same 4 instructors teaching the courses, but they're just using better teaching methods. And as a result, they have about a third the failure rate that they used to have for these courses. Now, most of the research in these fields has been done with introductory courses. That's where more students are. But my group and a few others have been looking at applying these same basic teaching principles, ideas to more advanced courses. And we see they also have clear superiority in that context as well. And, you know, these are smaller upper division courses in physics. They're much more mathematical. So almost all the work is students completing worksheets, having to write out solutions and answers, but again, working in small groups while the instructor is monitoring them, regularly giving them feedback. And just as a note, now almost all the Stanford undergraduate physics courses have switched to teaching this way. So just as an overall view, there's a structure of these kind of research-based classes that we've seen now works pretty well applied to virtually every subject, every class level, and in fact class size, and that's shown here. And this starts with the students doing some sort of modest preparation for class, and the instructor creating these practice tasks that is going to give the students to work on, then introduces the students to the task for the day. And then during class time, I guess not shown, yeah. During class time, the students spend most of their time working in small groups, 3 or 4 students each, then completing the activity while the instructor's circulating around, monitoring how they're doing, listening to those conversations, occasionally answering questions. And then at some appropriate period after typically 10 or 15 minutes of student work, the instructor will pull the whole class together, then give them feedback on how they're doing, answer questions, sort of sometimes provide new information that students are going to need to solve the next part, bring all the class back together. And then after that feedback session, then the class returns to the next set of activities they're going to work on, and class just continues with that cycle of student work followed by feedback. So the 2 essential features of this kind of teaching are, first, the students are spending their time thinking, practicing the reasoning that you want them to master, thinking like experts. And the instructors are much more knowledgeable about that thinking because they're monitoring much more closely what the students are doing and thinking. And so they can be more effective at their teaching. So, okay, those are just a few examples. I was able to collect nearly 1,000 examples of evidence of research studies from across fields of science and engineering comparing the traditional lecture method with this kind of research-based teaching, or active learning, so often called. And the active learning consistently shows greater learning and lower failure and dropout rates. Now, the data is almost all from science and engineering, but I think from the basic principles about learning that we understand at this point, we can be pretty confident that these apply much more generally than just science and engineering, but the data is overwhelmingly just from those fields because people just haven't collected data in other subjects nearly as much. Okay, so let me move to the third part about sort of more details about research shows is important. And this talk or this figure is sort of an effort to kind of organize all the education research into one image here, where at the core is sort of the center where the students are learning through their practicing solving problems with good feedback, where the good feedback is feedback which is timely, specific, and actionable, so the student knows what they need to do to improve. But then across the top are boxes that contain things that the research shows are important in the design of these good practice activities. And then the bottom are boxes are research about the most effective ways to actually implement these things in a classroom setting. And so I don't have time to talk about all of these, but I'm going to just touch on a few of them that are particularly relevant. But I just want to say that, you know, this box in some sense defines teaching expertise in a way that one couldn't have done 20 years ago, and that it really gives a set of methods that if a teacher knows and uses these methods, they're consistently going to get better student outcomes than otherwise. Okay, so let me first start about the disciplinary expertise. What is the particular thinking that you need the students to be practicing? And what I'm going to claim is that it's in science and engineering, and now I'm going to get more specialized, it's technical problem solving, that scientists and engineers mostly spend their professional lives solving problems, whether that's, you know, explaining phenomena, creating new things, or answering questions, etc. They're always solving problems. Now, and I should say in many other fields, you could argue much the same thing, but I won't go into detail on that. Now, the traditional way of teaching problem solving, though, is give a student a problem, they try and solve it. If they fail, you give them another, they keep trying until maybe they're successful. But the fact is that technical problem solving is a very complicated task. It involves many different aspects of thinking. And so this trial and error approach is a very inefficient way to actually learn. And so my group has done a bunch of research on the nature of technical expertise and problem solving that we think helps actually guide this process, guide the learning process better, in that it really identifies problem solving sub-skills that are sort of smaller pieces to students to practice and learn. So what this comes from is we did these very extensive interviews of about 50 successful scientists and engineers about how they solve some authentic problem in their field. And so we really dug into the details of how they went about solving them. And we found that their solving process was defined by making a set of decisions with limited information. But the thing that was most striking to us is we found it was the same set of 29 decisions. These 29 decisions were almost universally used across all these different fields of science and engineering for every problem that they went to solve. Now, if you're familiar with different fields of science and engineering, you might think that sounds crazy. They seem so different in what people do until you actually look at what these decisions are. The things like, you know, looking at a problem, deciding what concepts are relevant to solving the problem, deciding what information is needed and how to find that information, deciding what simplifications and approximations are appropriate. Once you have information, deciding how credible the information is and what conclusions you can draw from it, etc. And so once you see the nature of those, it makes a lot more sense that, oh yeah, these are going to apply really very generally. And so here's actually the full list of 29 decisions, and I'm going to give you just a minute to read through these as best you can. And so you can see, get a better idea of what is contained. So I'll give you a minute or so to read, and then I'll continue. Okay, so hopefully you had a chance to get through most of them, and I meant to say that I wanted you to, as you're reading through them, think about in your classes as a student or classes you might teach as a professor, think about how many of these decisions are you actually practicing in your course. Because I would claim that all of the, I sometimes ask people to say which they think are most important, and I get a whole big variety of answers because all of these are essentially essential for serious problem solving. They're always used. But I think the important point for learning is I would claim these individual decisions make up these sort of sub skills of technical problem solving. And so that as a much more systematic, efficient way to learn problem solving is to individually practice and master these, first individually and then collectively. And so if you, almost everybody, you think about, okay, these are very general decisions. What's the role of knowledge? And also what makes different disciplines different if they're all making the same decisions? Well, although the decisions are general, the making of the decisions always calls on specialized knowledge. Knowledge is particularly relevant to the context of that problem. And that's important for learning because what we see in our studies is that these experts have their knowledge organized really in the form for it's optimized for making these kind of decisions. And so that means that they learn knowledge, but they also learn it very much in the context of how it's actually to be used to solve problems. And so that's relevant for learning because in too much of teaching is kind of giving people a lecture on a whole bunch of knowledge that's saying, okay, you're going to need this someday, it'll be useful, but it just kind of sits there in the brain inert, never really gets called on. The way one really needs to learn knowledge is probably given a problem first and then see how knowledge is needed to solve that problem. And so you see not just the knowledge itself, but really how it's to be learned and how it's to be used. So just to summarize, I would argue good, expert in science and engineering thinking really at every level needs to be involved this extended practice at making these problem solving decisions using the knowledge and reasoning of experts. And just as a little piece of research about teaching the decision making, we did an experiment where we compared telling students what the decisions should be. That's, an awful lot of traditional teaching is taking that form of here's the right answer. But we compared telling students what the decision should be versus telling the students, here's a decision you have to make. Now practice making that decision. And in subsequent tasks then, seeing how well students actually could make relevant decisions to solve problems, there was just an enormous difference with the ones who had actually practiced making the decisions vastly superior. So that's just an important point about knowing how to best teach this. Now, in fact, what we've done at Stanford, and in particular, is to help students with this, we've developed a problem-solving template that gives them a selective set of decisions that they actually work through in a systematic way consistently when they're solving problems in class, doing homework problems, etc. And we developed this for an introductory physics class, but it's been so successful it's now been used for 5 different science and engineering courses and more every day. And so this template, it has parts of it. There's a number of decisions involved in problem framing, identifying what you actually are trying to do, making decisions involving making up a good solution plan for how you're going to go about solving the problem. Then there's a few involving the execution. And then there's reflection, thinking about, does your answer make sense? Could there be a better way to do this? is your approach working or need to be changed? So I'm not going to go in detail through this. Is this just an example of a way to make it systematically have students kind of give them a way to consistently practice making individual decisions as a way to then develop their overall problem solving skills. Now, I want to flag another concern with a problem with standard ways of teaching, and that has to do with looking at the kind of homework and exam problems students are given and what level of expertise and decision making are they actually giving students practice at. And I'll start by, if you look at sort of these, I listed 5 decisions here, which are essentially ones that you'd have to make for any authentic problem that anybody's ever going to face with solving. They'd have to make these 5 decisions, and then look at what the standard classroom, what I'd say is the sort of artificial problems that students are given to solve. And so, first, in a standard textbook, all the information needed is given and only that information. So that eliminates the need for practicing, recognizing what information is needed. The students are told what to assume or, neglect air resistance, etc. That eliminates the simplifying assumptions. They normally, it's a chapter 3 problem, so they'll use chapter 3 concepts to solve it. So that takes out the deciding what concepts are going to be needed. And then they only call for one representation, so they don't have the practice of figuring out what are most useful representations and that use. And then they're only just asked, okay, give an answer, a numerical answer. So that takes out the practice at testing and justifying their solution. So we've done more systematic studies of this across a number of different physics courses and find that the standard problems involve students actually practicing very few decisions. And I emphasize very few of these decisions, that as the students go out in the real world to solve real problems, that it'll always need these practice on these decisions. So, the answer is you need problems that have better, more decisions. And this is just a quick example of a type of problem we've created for our introductory physics class that is, we call it a real world problem. It's the idea with a IKEA dresser, the students hanging from the, or children hanging from the front can tip the dresser over. The problem is, okay, how strong does the support need to be to hold against the wall? So it's a good standard physics problem, but it requires many more decisions than kind of the typical artificial textbook problem. They have to think about, which concepts to apply, how to apply them, what assumptions to make to simplify this, what information is needed, how to find that information, etc. This sort of thing that, like I say, this is a real world problem, puts in many more decisions. Okay, so I'm going to move on here to talk a little. I'm going to skip over prior knowledge and experience and motivation. I think those are important, but they're kind of obvious to people. You need to kind of match and build on students' prior levels of prior knowledge, and you've got to motivate them to put in hard work. And this is where a lot of the variation across students that are based in past experience comes in, that makes it challenging for teaching. But I want to say something about basic constraints about how the brain works. That this is very well known to cognitive psychologists and very unknown to most university teachers, but it's very important here. And it has to do with the basics of how the memory works. And so the memory actually has is the simple model of it is 2 parts. There's the long-term memory, which is what most of us think of when we think about memory. And this has, very long duration. You remember things for decades, and enormous capacity. You remember a whole lot. But in addition, there's another component to memory called the short-term working memory. And this is kind of a buffer that information has to go through before it can be processed and go into long-term memory. And this short-term working memory, at first it's short-term, it operates on timescales of minutes, but it also has, most importantly, very tiny capacity. A typical human brain, about 6 items at once. It's really how much your brain can pay attention to at once. And because of this very limited capacity, when the brain hears or sees something new, gets anything that gets its attention, it actually pushes out what was already in that working memory. And so that thing that get pushed out never get illustrated here, never get processed and into long-term memory. And so this has many implications for teaching. One of them is just why it helps you understand why breaking expertise down into these simpler pieces of sub-skills for deliberate practice is because if it's a lot simpler, the brain can keep track of all the things it needs to be paying attention to for completing that task. Whereas you're just trying to solve a whole complex problem, there's just way too many things for the brain to actually keep track of at once. So it's important in that, but it's important in many other things. In general, in teaching, one of the important lessons is that everything that uses attention or causes the learner to pay attention to has a real cost in learning. It displaces something else from working memory. And so it reduces whatever got pushed out, reduces the process and learning of that. And so there's some things students can do that's really bad for this. And one of the worst things is split attention, checking your cell phone or looking at a computer while you're supposed to be learning something. That other attention takes up a whole lot of working memory, and it's well studied that it's just a disaster for learning as a result. But there's a lot of things teachers can do that also kind of take up working memory. If they introduce unfamiliar jargon, they're just covering way too many topics. This is one of the primary reasons we measure so little learning from lecture. It's way more than the working memory can actually absorb. But even things like, making that picture look prettier by putting a little added stuff to it, or the thing that gets the most concern when I mention it is even those digressions or little jokes. If they take students' attention, they actually can hurt learning, and there's data on this. Okay, let me say a little bit about the research on implementation of these things in classroom. First is it's important to have good tasks, one that are appropriately challenging and practice the thinking you want them to learn, but also to have clear deliverables, things the students has to actually complete to carry out the task is important. But then I want to say a little about the value of the social learning. I just kind of quickly mentioned in passing, almost all the research has shown that we get better learning when students are working together, optimally as groups of 3 or 4. And you need to understand why that's effective. And a lot of times when I tell professors about this, they find it hard to believe that, students talking to each other, that should be more valuable for their learning than actually listening to, the expert instructor explain things. But the fact is, it is more valuable, and there's a couple of reasons for that. One is that the students can provide each other with much more individualized feedback. They might not be able to cover everything that they need feedback on, that some things just more complicated, you need the instructor, but a lot of simple things just that a fellow student can help you with in a way that in any reasonable sized class the instructor is never going to be able to do. But there's a more interesting and arguably more important aspect of this, which is that the idea of teaching or explaining something to another person triggers a different set of cognitive processes in the brain. The brain has a whole bunch of, circuitry associated with social interactions. And so if you're planning to teach something to somebody else, you actually think about it in fundamentally different ways. And people have been able to show that this kind of thinking about teaching to someone actually contributes more learning than just studying it yourself. And so there's really a very direct beneficial process to this social interaction, to the learning process. And then of course it's useful for a teacher to sort of be able to listen in on those conversations and get Stein's idea. I want to stress though that we study, work a lot with students, and there's a lot of opposition to students to group work, aren't usually because they've had very bad previous experiences. And one of the reason it can fail really is that groups aren't really coached how to behave. And so it's really important to, if you're going to use groups or work in small groups, to have norms of behavior about how people should work, how people should behave to make the group work effective. Okay, so now I'm just going to finish up almost on schedule. A couple of comments about artificial intelligence. And I think artificial intelligence has raised two questions really that are quite different. One is what students should really learn in the age of artificial intelligence when they can look up so many things or just ask the AI. And the second is, what can AI do in actually helping the teaching and learning process? So the answer to the first question of what students need to learn is, my real answer is I don't know. I think we're still figuring out how to best use AI as a tool to support scientific thinking, really, and to decide what can be left to AI and what not still needs to be in the human brain. And I think, fundamentally, we're just going to have to see how, over the next few years, how engineers and scientists come to collaborate with AI and how to do it effectively. And then we're going to have to train students how to do that. However, I do think there's almost one place that's very likely that AI is not going to replace the human brain, and that is that making these judgments, these decisions where you have limited, insufficient information to know exactly what should be done. AI is very good for providing knowledge, for providing things with well-defined solutions. It's not nearly as good at making judgments where there's incomplete information, which is almost always the case there. So I think for at least the foreseeable future, that's going to be still the place where you need to learn and be useful of using the human brain. Now, the second part of how AI can help teaching and learning, my group has been studying this and doing research on it. And I'll just say that I think the hype around this is way inflated, that AI is good for providing information, and so it provides answers. That's not really very effective teaching. Effective teaching is helping people understand how to change their own thinking. And so, there's kind of a fundamental problem with the design of AI, of how to provide good teaching and feedback. And so we're making actually quite a lot of progress in this, but it really requires a whole bunch of human intelligence that's got to go into guiding the AI into how help it interact with students in a more effective way for teaching. And so I think we're far enough along that I'm pretty confident it's going to be useful as an assistant, but it's very far from replacing the teacher, that you still need to have a lot of teacher resources go into guiding it. Okay, this is another form of AI that using interactive simulations, I think I'll just skip over because I don't have enough time. And then I'm also going to skip over a section on administrators just saying, this is involving how one can make change in teaching on a large scale. And we launched an initiative that was successful at changing the teaching of many hundreds of science instructors, actually. And so we showed it really was possible. Once people learned to teach this way, they liked it better, and it didn't cost any additional money. But it really requires the institution to recognize and support this kind of more expert-like teaching. And the teaching evaluation is a really serious problem. You're going to need to have teaching evaluations that capture better about whether people are using good practices rather than just whether students are happy. Okay, so I'll finish with that so that it leaves some time for questions. Just to conclude, I think the research shows what good teaching design and implementation is like, and how and why it's better than the traditional lecture approach. And that the key idea is really that it's giving the brain practicing and developing it accordingly. So thank you for your attention.
We'll use this one. Thank you very much. It was very inspiring. So we have, the microphone is coming down. Are there questions from both teachers and students? I have many, but someone daring? Achille, Professor Giacometti.
Yes, thank you very much. Within experienced teaching professors like in my own generations, there is a widespread narrative which I think is wrong, but it goes like this. Well, if you use this method, you are actually watering down the level of the course. So I think it's wrong, but I don't know how to address this concern. Maybe you can give me a suggestion.
Yeah, so I mean, there's two aspects of this. Let me say. I mean, you say there's the concern about you're watering down the material, making it too easy, if you like. The other aspect that I'll comment on, because it comes up very oftentimes, is how do you cover as much material also? And so the watering down, I mean, first you're making the learning process more evident, and so it's more efficient. But would you say, nobody would say that you're watering down learning to play a violin because you're telling somebody, they've got to hold their fingers in a certain way, the bow in a certain way, as opposed to telling them, go learn to play Mozart symphonies. I think it's just just one simply works a lot better. And so, on the one hand, it isn't like they had, and it's more efficient, and students can learn a lot more. And so, it may be making it watered down if people can learn easier and better, but that's what our job is, to make them learn easier and better. So the idea of the covering the material, I mean, we actually studied this quite carefully in this big program I ran where we were trying to change teaching a whole lot of courses because we wanted to see. And you do need to think carefully about how you use class time to cover material in the most effective way. I mean, it is true, if you're especially using PowerPoint slides, you can cover in 1 hour and 200 slides, you can cover a vast amount of material, but the students won't learn any of it. And so what we've found is, if you do it carefully and you think carefully about your coverage and what you're having the students do, you can cover just about as much material. But you do have to give some thought as to using the class time efficiently. But back to the question about watering down too easy. I mean, these problems we give the students to solve, they're challenging. They're hard. You look at the IKEA dresser problem. Okay. Most introductory physics students have no idea how to start doing that problem because it calls them to do a whole bunch of problem solving. they never had any practice doing. And so they're learning a lot more things.
Yes, Michele, here. Professor Bugliesi.
Yes, thank you. That was really inspiring. I go back to the same question, essentially, which is the second part of your answer. To what extent do you count on students, on flipping classes, so assuming that the students have read some materials ahead of time when they come to class?
Yeah. So the preparation for class, first I should say that really depends on the class. Sometimes the instructors will give sort of a brief lecture preparation. Other times, particularly when there's a textbook that's appropriate, they have them cover. We studied this systematically about how to ensure people prepare for class. And, what I can say is we found certain things you can do that ensure that 80+% of the students would always do the preparation. Okay. And so one of them, first thing is to have be reasonable about what your expectations are. Don't have them read all of 50 pages of chapter 4 where you're only going to need to know a third of it. Textbooks are always bloated with extra material. So be targeted in what you're asking them to do, and so that's reasonable. That's one thing. Second is give a very brief, typically 3-question online quiz, very simple to do if you've done the reading, but you do need to do the reading, and give them some very tiny incentive. It doesn't take much and they'll do it, but just shows you care about it. And then the third and most important thing is don't start class by saying, well, you were supposed to do this reading and preparation for class, but I know a lot of you didn't do it, so I'm going to tell you what was in it, so that way you've just punished everybody who did the reading and rewarded everybody who hasn't, and so they will immediately stop doing the reading and wasting, because you're just wasting their time. So, but those, like I say, we sort of systematically studied that and found that if you do those 3 things in a whole range of classes, we saw that quite successful. Yeah, back.
There was some hands there.
Yeah, up and back. There's these microphones and come in sort of
balls.
They can just throw around. It's really effective.
Hi. With respectfully, in the 1990s, when you were doing the Bose-Einstein condensation research, so what gave you that confidence to keep going on that, with the uncertainty and the competition? And now, because of the AI competitive world now, what the young researchers recognize a problem with that level of commitment? How can we give that level of commitment now?
So, the commitment to keep working on a hard problem like Bose-Einstein condensate, that was following a research project that was much harder. It took me 15 years to finish. And, I don't know what to say about that. That's largely a kind of personal psychological value that, willing to keep beating your head against a hard problem for many years. So I don't know any clear guidance for how to learn to do that. It's just a question of whether one feels that way or not. I don't think AI has changed that aspect at all. The idea of being willing to struggle, being willing to put up with frustration and keep going, trying to go forward is still the same, I think, whether AI or not. There's a question in back there.
So I saw a lot of graphs, but I was more like I was interested on knowing if there is in the study there was a part where you analyzed the efficiency of the method with respect to the size of the classroom. Like, is there a limit on how big the classroom needs to be for this method to be effective?
So there's no real detailed studies on class size. We have sort of here. Well, in the middle there, you can be giving him the microphone while I'm answering. So, what I can say is, it's in a smaller class when you have movable tables and chairs. It's certainly easier to implement these methods, but we've seen that with some care, you can implement them in a big lecture theater like this as well. But anecdotally and personally, we've seen that once you get more than about 200, things stop working as well. And I think the reason is, and it's possible technology could help with this, but my personal feeling, without any detailed research, is that the problem when it gets too large is that you can't have a classroom discussion anymore, because students in one part, if a student is making a comment or asking a question in one part of the class, the students in the other part of the class can't hear it. And a lot of the kind of classroom interaction sort of then breaks down into sort of separate little independent groups and not sort of seriously involved. So that depends some on the layout of the room, but I'd say in most rooms, 200, above 200, you start to see that people have noted that difficulty. Yeah. In the
Yes.
Yeah. Okay.
So,
Okay.
If you
Yes.
stand up, we see you.
okay. So I have a quick question, and so I want to say I'm an engineering physics student. I had the chance to experience these methods, innovative methods, through Professor Bonetti, and so I want to ask. I would say there is a mentality problem here in Italy. We tend to be much more conservative rather than the US, just to say. And so I would say that in Italy, Italian professors tend to be much more stubborn when it comes to changing their teaching method. So I want to ask, what would you tell them?
Yeah, so first, I'm not at all sure that I think you're right. There's lots of stubborn U.S. professors I talk with. It's hard for me to know exactly what to say. I give talks like this a lot. I try and show them data, basically, and show them that there's not just data that supports this in comparison, but also underlying principles about learning that really support this way of teaching. Is that sufficient? Well, it depends a lot. I find that what matters more is if they can actually observe a class being taught this way. That tends to, a lot of their fears about things that could go wrong tend to be a lot less than, and they see how much more engaged the students are and how teaching is therefore more fun. Nobody likes giving a lecture to a half-empty room full of students who are mostly asleep. So when students are engaged, interested, asking more questions. So that helps a lot, but there's no magic. I have certainly not found any magic message that converts everybody. It's sort of a slow process. Yes, okay.
Hi. So first of all, thank you for such an amazing talk. My question is, how would you say, or what suggestion would you provide when one is approaching a problem as a student? Because I feel like when you're in science, you're a student of the game. You're a student for life. I personally, sorry for taking too long, I always think back at something Neil deGrasse Tyson said, that a scientist is a kid that never grew up. So my question is, as a student and as someone who thinks he's a kid that never grew up, what else can someone do to approach a problem, maybe even a problem that not many people are tackling?
Yeah, so the way that we've really taken to help. I mean, your question, I think, is true of almost every student, really, at some level, at the particularly the university level. They've gone through high school, and in our case, you know, they mostly learned to kind of memorize procedures, and that took them fine through high school, and they get to college and they're actually solve problems, and that's a whole different thing. And you know, so the approach we're taking is to help support them by breaking the problem down into these decisions and how to look at these very specific decisions, you know, how to graphically represent what's happening, deciding what information you needed, deciding what concepts are going to apply, etc. And so, you know, I would say that, you know, as a kid, you're sort of curious about how to do things, but that doesn't help you solve problems, really. That just makes you interested in how you might solve them. And I think this process of thinking about the decisions involved is a way to systematically think about how to approach actually solving.
Thank you so much for your talk. I would ask if you have any method to make the level from the students that come from different cultures or even different high school teaching levels, because we know that we have some high schools that are more engaged into science, but we have other schools that are more engaged into human field. So how to do that from each person arrives in the final objective?
Yeah. So, you know, that the level I would rephrase this as sort of, how do you deal with the different levels of preparation of the students in the class? And frankly, this is always the biggest challenge that teachers would face. You know, how do you have tasks that are challenging for some of the students, but not completely impossible for others? And, you know, I wish there was a perfect solution for it. We keep struggling on how to improve. And so, you know, I'll just say there is no perfect solution for it that anyone I know has found, that it's always an issue, but there are certain things that can help. And one of the things that we've seen can help is this working in small groups where the students can kind of leverage each other's knowledge in that case. And if a group is working well, and this is kind of get back to my stressing how you need to have norms of behavior but if a group is working well, then you know, that can help students who are less prepared, can get sort of more support from the other students and more individualized help, and so that makes a difference. This process of making the learning process more explicit, so by breaking the problem down into these decision-making steps, you know, again, you're making the learning of problem solving more efficient for everybody, but you're particularly helping the less prepared students, because less prepared in the subject also means less prepared in how to learn the subject usually. And so those are two aspects that we are pretty confident make a difference. But it's still always a challenge. I don't mean to say that we have any great answer. You know, we hope it maybe AI can also provide some help, but there's challenges with that as well.
Well, thank you. I wanted to know, well, from your talk, I gather that you really value physical presence and physical interaction, relative interactions between not only the teachers and the students, but the students themselves.
Yeah.
How do you see the blending of recorded content by teachers, or the only recorded or courses that can be erogated.
Yeah.
How do you think they can be used?
So I'm frankly very skeptical about the value of these completely online courses where it's all recorded and the student just listens to recording. I'm skeptical about that for multiple reasons. I mean, one is we know that from data, that just listening to lectures usually is a very ineffective way of learning. It's almost certainly less effective for online when you're listening to a computer because of this idea of split attention. There's just, you're listening to the computer, there's so many other things that are just more likely to distract you in that case. And so, so personally, I'm just very skeptical about the effectiveness, and some of the data shows this, that, these pure what I'd call asynchronous, because there's not instructor there, they work for very well prepared, very highly motivated students, and not very well for anybody else, which is, everything works well for well prepared, highly motivated students. So, I think synchronous online learning can be effective, where you do have the instructor there, you have the students there at the same time. You can go to breakout rooms and so on, where the students are actually talking to each other, the instructor's listening to be able to listen to them, and so on. So I think that can be effective, but this idea where you're just listening to online lectures asynchronously with no other students around to discuss it, I'm very skeptical that they're very effective educationally. A lot of those, again, are sort of based in the fundamental principle that learning is just about pouring knowledge into our brain, and that just isn't the way it works. So,
first of all, thank you, Professor, for your lecture and for sharing the research with us. My question was about if there are some results of applying this method to lower levels of instruction, especially to compulsory school, where I think the big challenge is that you are not teaching to people who want to listen what you are teaching, and probably those are the people that would most benefit from understanding the concept. Thank you.
So personally, I've strenuously avoided working at that level because it's so much harder for the reasons you say. There's these many other factors, and what I would say is we have some research showing that these ideas will apply at that level, but the research is much messier because, for just the reasons you say, there's so many other factors involved in the school and school environment at the lower levels that it makes it much harder to get clean research data like I presented, like we can get from university. So I think we can be pretty confident that the ideas are going to apply, but they're just other factors that come in to make it more difficult sometimes, as you say.
Hi, thank you for the inspiring talk. I'm an instructor from the humanities, and I wanted to ask you, whether you would have any ideas on how to scale this methodology up and have it generalized across fields. Because you mentioned that there is no data available for application of such teaching methods to other fields. But I was wondering, is there any tailoring that could be made to apply such methods also? I teach Arabic language and linguistics, and I would have a hard time figuring out how to have my students do problem solving for history-oriented courses. So
sorry, I missed what subject you're teaching?
Arabic language and linguistics.
Oh, okay. Language. Yeah, so I don't know about language. I mean, I know, social sciences and so on, it clearly pretty directly applies. Even things like most of the humanities, I can sort of see they involve solving problems. Languages, I don't know. I mean, I will say the other aspect that I know about languages that makes me wary of giving any advice about it is that the brain has so much special language specialization. You know, there's a whole bunch of the brain just devoted specifically to language that doesn't carry over in other things very much. And so I mean, I just know of those differences. It makes me very wary of trying to give any advice on languages,
Yeah,
to
but
be honest.
beyond languages like humanities in general, do you think that's something that can be scaled up to the other fields as well?
I think in like I say, you know, many other subjects, you know, economics, finance, social sciences, I think you can see pretty directly how these ideas would apply of giving students problem, working together in small groups on figuring out solutions, you know, that having them practice the thinking you want them to learn. I think you can see that it would apply fairly directly. And some people are doing that. And I know actually in economics that now is sort of a growing movement of this kind of economics education research. So
Maybe last 3 questions we have. 1, 2, 3.
Okay, thank you for the very inspiring talk. So we go back to physics now.
okay.
So, I mean, you talked about the normal behavior, but how do you ensure that actually students in small groups are work according to the rules so that you set, or even when they have to work by themselves, how do you make sure that they are doing their homework, they want to do it? And on the other hand, I feel that there may be a little bit the problem that students, they feel that they are under exam during these small exercises that you give around. And this may be like, I mean, I don't know, it may be something that blocks them from applying the correct reasoning because they might feel like, oh, I'm under examination now. The teacher will remember about me, like about the mistakes that I make. It will get bias and this sort of reasoning.
Yeah. So the second problem of kind of the students feeling that that we've never seen that to be a significant issue, and in part it's how you treat. You know, they have to do something. I said we want to make them have to do some deliverables, but how you process those deliverables. You know, in fact, we usually have felt that we would have liked to do more grading, if you like, more feedback on what they're doing right or what they're doing wrong than we actually are practical to do in a large class, because it's lots of material. And so we do fairly minimal marking of that. You know, mostly it's just if they've done it or done something reasonable or not. And so anyway, just with that way of handling it, the issue you said is pretty we just never have run into that at all. And you know, exams are a whole different issue about how you handle exams and so on. And I always felt that it's important to have them very closely connected with what the students are practicing doing in class. And, you know, then they worry about exams, but they don't, we've never really seen them feel pressured. Now, in terms of making sure the groups are working effectively, this is something though that the teacher needs to do. And, you know, going around and monitoring what the students are doing, you also monitor how the groups are functioning and intervene at times. The main intervention is really when somebody is really dominating a discussion. You know, as an instructor, you sort of need to encourage students who aren't speaking up to speak up and encourage some to stop talking as much. And usually with very little intervention, that is sufficient in my experience. But that is something that a good instructor will be doing as they're monitoring the student work. They'll be monitoring also how the groups are functioning.
Hi, I used to work in a middle school as a teacher, and I saw that adding some funny moments during the lessons could help the students to relax for a moment, take a breath, and then refocusing, and then be more involved in the lesson. So I know that the university lessons are really different from the middle school, but do you think that this kind of approach can help the learning of a student?
I don't really know. I'm inclined to think that something like that is much more important at a middle school level than university level. That students are sort of more mature and probably don't need that, but I don't know, really.
Thank you very much for the talk. I really appreciate it. And my question is in regards to the setting of education. I'm wondering if whether it is appropriate to consider that we currently have an optimal setting for learning. Our classrooms, should they change, or is that setting optimal for learning?
Yeah, so that's the question about the classroom setup,
okay.
and you're absolutely right that a classroom like this is not nearly as optimum as one that has a bunch of separate tables with chairs that students can sit at and talk easier with each other. So.
Yeah, I meant more in sense of maybe music or other, just more colors, just like differences. Or is this not something
I'm
you've
not
considered?
sure I'm
Okay.
following your.
Oh, mainly because I'm wondering if more external influences can affect the brain learning and setting in a different way. So music maybe changes something, or just the colors.
Okay. So
Yeah.
So different modes of presenting material. Yeah. So this is I'm not sure I'm answering your question, but there is sort of this idea of what's the term I'm looking for? Too much jet lag. Styles of learning, where some people they think it, presenting material visually versus verbally versus other ways is kind of more effective. And the research on that shows that it really doesn't matter. Ultimately it's what happens within the brain, and so it's kind of the mode of information coming in is not very important. It's just what the brain ends up doing with that information that matters. So I don't think that's probably answering your question very well, but I'm not sure how to do any better.
Thank you very much. I know there are other questions, but we have a long program, and I think we fill it up. But thank you so much, Carlo. It was so inspiring, and thank you also the audience for the many interesting questions. Thanks again.